Well, all right. So as you can see here, I've now added a new statement, A triple bar B horseshoe A. Now, of course, you'll notice that I've used the same letters here as in this other statement. So because of that, we can use the same pool of values over here. We don't have to reinvent the wheel. We don't have to come up with a new pool of values since we'll be using the same letters over here. So we're just going to practice this again, make sure we're getting the hang of doing an ordinary truth table. And then also, by developing an ordinary truth table for two statements, we'll be able to talk about some other definitions here that will apply. Having said that, I also want to say that one of the themes here in 5.3 and in this specific lecture is to think about ways we can speed this process up, right? The way we did this one here worked fine, and it's great, but it does take a lot of time to sort of think about each of these T's and F's as we're placing them here. And so as we go along, let me give you a few tips here as to how to speed this process up a bit. So the first way to do this is, once you've got your pool of values here, and by the way, that's always required whenever I ask you to do an ordinary truth table. And I know right now I haven't talked yet about any other kind of truth tables, but in 5.5 we'll talk about indirect truth tables. And when you do an indirect truth table, there is no pool of values here. I suspect that after we talk about indirect truth tables, you'll actually probably tend to prefer them to ordinary truth tables because they're a little bit quicker. But I want to emphasize, I will want to see that you know how to do both techniques, ordinary truth tables and indirect truth tables. And so when I ask you to do an ordinary truth table on the exam coming up, make sure you're providing me with that pool of values as I'm asking. Okay, so having said that, we've got our pool of values. Then we want to come over here to the statement. We want to identify the main operator. And again, I hope that I've made this fairly clear. The parentheses here tell us that this triple bar will be the second most important operator, meaning then that our horseshoe will be the main operator. So we're going to save that for last. And so since we're thinking about this here, we might just quickly realize then the order of operations will be, right, our A and B will feed into the triple bar, and then whatever we get for the triple bar will be feeding in to the horseshoe here. Right, so hopefully you can recognize that. So here's a way to speed this up, though. You saw in the first statement here we did it row by row, but instead what we're going to do this time is we're going to actually transfer this information here from the pool of values, transfer it over column-wise. Right, so I've just taken the pool of values here and plugged it into these columns. And that enables us then to, well, we're not going to worry about the horseshoe. That's the last thing we'll do here. We can worry about the triple bar, and we can just sort of rip through the triple bar here, and we can just focus on, well, how does a triple bar work, and work that out. So in other words, we'll just remember that for the triple bar, it is true when both sides match. So true, triple bar true will be true, but when the two sides are different, it will be false. And so here they're different again, it will be false. And here down at the bottom, they're both false, and so that actually makes it true underneath the triple bar, right? They match, so it's true. So by doing it column-wise, you can just focus on a particular operator and you tend to get through that fairly quickly. Now, as we've already indicated up here, we now want to take this triple bar column and feed it in to the horseshoe and then the A values here from the right-hand side. So in other words, we're looking at true, horseshoe, true, and that will be true. False, horseshoe, true, also be true. False, horseshoe, false is actually true. And then finally, true, horseshoe, false, right? Hopefully, again, that rings the bell in your mind. That is the one and only way to make the horseshoe false. And so we get all true and then false here in the fourth row. And so we can then know, I hope, based on what we saw over here, that once again what we have is a contingent statement, since we have some T's and some F's underneath the main operator column here. Now, having done that, we can then move on and actually think about the next slide here, if you're looking at the PowerPoint slides, but the next bit of information from 5.3, and that is what kinds of definitions apply to multiple statements. And so the first one there would be logically equivalent. In other words, two statements would be logically equivalent if they match underneath their main operator columns precisely. So true, true, all they match. True, true, false, true. So because in this third row they do not match, it only takes one row to do it, these two statements are not logically equivalent. Just to be absolutely clear about this, if we had some other statement here, just some random statement that we worked out, and it came up with true, 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 and false, we would then say that this statement right here is logically equivalent to that one, right? Because underneath their main operator columns, they are precisely the same in terms of their truth values. So that's what logically equivalent statements would look like. These two are not logically equivalent. I hope that's clear. So if these two are not logically equivalent, what might they be? Well, the second thing we can ask is, are they perhaps contradictory? Not self-contradictory, mind you, but contradictory, right? Self-contradictory is when underneath the main operator column it's always false. So contradictory statements happen when the two main operator columns are opposites in every row. And clearly, true, true, they're not opposites in every row. And so these two statements are not contradictory either. Again, to be clear, if you wanted to see what a contradictory statement would look like, if we had false, 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 and true for some made-up statement here, then of course with this statement it would be opposite in every row, and these two statements would be contradictory, right? In other words, they would contradict one another. Would be another way to put that. Okay, but back to these two then, the blue and the green statements here, they're not logically equivalent, they're not contradictory. The next thing we would ask then is, are they consistent? And what that means is, are they both true in at least one row? And of course, right there in the first row, they're both true. And so we know that they are both, or I should say, those two statements are consistent then, right? Because they're both true in at least one row. They are both true in multiple rows, but that only takes one to be consistent. Now, something to think about here. Let me change this again. Let's say we had some statement turn out to be all false underneath its main operator. Now, of course, we would know that individually that would be a self-contradiction, right? That's what that means. It's a statement that cannot possibly be true. But let me ask you, comparing this statement with this one, right? Clearly, they are not logically equivalent. That's hopefully obvious. They're not the same in every row. They're also not contradictory because they are both false here in the fourth row. So we could ask, are they consistent? Now, I'm going to pause here for just a moment to let you think about that, because it's important to recognize that these two statements would not be consistent. There is not at least one row where they're both true, right? So consistency is about truth. Could they both be true at the same time, as was the case with those two statements? Yes. But it's not about being the same in two rows, right? Yes, they're both false here in the fourth row. It's about whether or not there's ever a time when they're both true in at least one row. So these two statements here are not even consistent. So we would say that they're inconsistent. That's the terminology we would use. And so you'll be asked to think about the same thing on the exam. In fact, I'll give you 3 statements, and you will have to work out an ordinary truth table for all 3 statements, and then tell me individually of the 3 statements, are they contingent, tautologous, or self-contradictory? And then I'll ask you to compare 2 statements and tell me if they're logically equivalent, consistent or contradictory, or inconsistent. It won't be in that order. It'll be logically equivalent, contradictory, consistent, or inconsistent. So you'll be doing that same kind of thing on the exam. One more thing here to add about these terms that we're learning about here, comparing statements, is that, again, these aren't particularly technical terms, right? Certainly when we say that 2 statements are logically equivalent, what we're essentially saying is that they mean the same thing. When 2 statements are contradictory, we're saying that they could not in any circumstance both be true at the same time, right, because they have opposite values in every case. When we say that 2 statements are consistent, right, we're saying that they could both be true at the same time. Sometimes there's a little confusion between saying that a statement is consistent and saying that it's logically equivalent. And I will just add for that imagine there's been a collision at an intersection, right? And an officer comes to take witness statements. Well, if the officer is interviewing witnesses who saw the collision from different corners, let's say, different perspectives, one witness might say, well, I saw the person turning left. The other witness, if they said, their whole statement was simply, I saw the person turning left, well, of course, in that case, their two statements would be logically equivalent. They'd be saying exactly the same thing. That doesn't exactly happen all the time. One person might say, I saw the person turning left. The other person might say, I don't know if they turned left, but I saw they had their left turn signal on. In that case, those two statements are not logically equivalent. They don't mean the same thing. They would be, however, they would be consistent, right? They could both be true at the same time. Certainly, the officer would hope that the two witnesses' statements are not contradictory. That would be problematic, as well as it would also be problematic if they were inconsistent, right? If the two stories could not both be true at the same time, at least one of them would have to be false, if not both of them. So this terminology, though it does pertain to symbolic logic, is not unique to this domain, so do understand that.